Hi there, yes, you guys, engineers. Guess what? You've got a job. You've been hired by a company to update their transport service. What do they transport exactly? Organs. Human organs. Don't worry, you won't have to get your hands, dirty. You, as chief engineer, along with your team, just need to redesign their currently inefficient vehicle for the purpose of traveling up windy and bumpy roads. I should mention that the medical center that requires these organs resides on the top of a mountain. Good luck fixing this. Don't worry, I'll help out. Let's get started. This vehicle has poor aerodynamic qualities, a deteriorating and over-engineered chassis, and poor suspension setups. Alright, this will require some work. First priority, let's get those body panels redesigned. Looking at all of the force vectors acting on the vehicle's center of pressure and center of gravity, we see that drag and lift really let this vehicle down. Drag reduces fuel economy and lift doesn't allow the vehicle to hug the road as it is cornering. The handling suffers because of such large lift forces, making this vehicle incredibly difficult to maneuver. Thankfully, you have a strong knowledge of vector manipulation. Knowing the direction and magnitude of each force vector helps to derive an expression showing which variables significantly alter the drag force. By reducing the coefficient of drag in frontal area, we can find which body panel shapes will positively affect fuel economy. Now, let's see how we can increase the downforce of our vehicle. By applying the same principles that we just used to reduce drag, we can look at the pressure distribution along the car and calculate the current lift force. By summating the forces in the vertical direction, we can calculate the amount of downforce required to lower the car. This allows us to strategically position front wings and a rear spoiler to create the extra downforce that we needed. Now it'll hug that road alright, and it looks pretty good too. However, our work isn't completed just yet. Oh no, the company isn't paying for a job half done after all. Let's move on to the chassis design. Since we changed the body panels, we need to redesign the chassis of the car. Of course, it should be strong enough to withstand the tough driving conditions, whilst keeping weight to a bare minimum. Taking into consideration the project's budget, you and your team have opted to go with a space frame chassis. In order to calculate the sections of the chassis which are in high stress, we can apply the finite element analysis, or FEA for short. These areas will suffer greatly from fatigue when external forces are applied to the chassis. Now, while there are plenty of software packages that can compute the FEA, that doesn't mean you can simply rely on it to do your job for you. If that were true, we as engineers wouldn't really have much need to exist, would we? Knowing how to compute the FEA yourself allows you to understand what it is you are doing and how to troubleshoot problems when they inevitably crop up. Engineers aren't always perfect, just mostly perfect. Damn, we're great. Okay, moving on. Thanks to the FEA we performed, we realized that we can remove redundant pipes from the chassis, and in doing so can safely say that we will not lose any strength and will be both lighter and cheaper. Alright, chassis is done and looking fine. We've got a pretty sweet vehicle if I do say so myself. Sweet and efficient. Suspension is the last aspect that we need to tackle. Well, in this hypothetical at least. Obviously, we're omitting about 95% of a car design, but you don't want to be stuck here all day, do ya? Moving on. Here is a simplified diagram of the vehicle. Using it, we can create an algebraic math equation. This helps us to find particular values of interest, such as how high the car is going to bounce after it clears a bump. In control engineering, you learn to replicate complicated systems into what is called a block diagram. The beauty of block diagrams is that we are able to represent complicated math equations as a visual language. This particular block diagram represents our vehicle's suspension setup. Here we can see the block diagram simulation in effect, showing us how the car responds to the road surface. By changing any value, we can immediately see how the response changes. In our case, we need to increase the unsprung weight to get the particular response that we're after. So, you can see that it is essential to have a strong understanding of mathematics and its applications. And And we're done. Nice work. You, well, we, don't act like I didn't help you out, have successfully redesigned a vehicle which can get those organs straight up that mountain in the most economical, efficient, and reliable way. Hooray! Well, unfortunately we can't always account for human error.